Hello everyone, my name is Runzhou from Fraunhofer ITWM and RPTU Kaiserslautern. Today I will present our work, Rendering Synthetic Defects for Learning-Based Industrial Inspection. So let me start with the background. In industrial visual inspection, the standard pipeline has 3 steps. Collect real defect images, annotate them, and then train a machine vision model. But in practice, this is difficult. First, real defect data is rare. Defects do not always happen frequently in production, and collection is costly. Second, annotation is hard. For surface defects, boundaries are often ambiguous, and creating precise masks require expert effort. Third, learning-based model usually rely on sufficient training data to generalize across different conditions. Real data alone is often not enough for robust training. This leads to a natural question. Do we have an alternative way? One possible way is synthetic data. Instead of rely only on real samples, we can train the inspection model with synthetic images. But this also raises a more challenging question. What kind of data do we need? In practice, synthetic defects should provide ground truth masks, scalability, diversity, and controllability. There are several ways to generate synthetic defect data. One direction is generative model, like GANs and diffusion models. These methods can synthesize realistic defects. Some modeled architectures can also produce pixel-level masks. However, they are often hard to control. In particular, it is difficult to precisely specify the defect structure, location, and variation we want to generate, and hard to decouple different factors. Another direction is procedural modeling. It is attractive because it gives us explicit control over modeling and rendering parameters. One option is geometric-based modeling. We modify the mesh directly, and the defect is physically explicit. But for small specific defects, this can be computationally expensive. Another option is bump-based modeling. We perturb surface normal and shading time. It is less physical, but much easier to scale. Now we have the scalable and controllable tool for defect generation. However, how should we design a training dataset? In practice, we first use real defect images as visual references. Then, we turn the modeling and rendering parameters to reproduce similar defects. But for training, match a few realistic-looking examples is not enough. We need to expand parameters to generate a large training dataset. Domain randomization suggests that variations can improve generalization, but it does not tell us how much we should vary each parameter. So the key question is, how should we choose the parameter ranges so that the generated data actually helps the model learn? This is the main focus of our work. Here, we propose a shift in perspective. In conventional rendering, the observer is a human viewer. Our focus is often on matching reference images, and the goal is visual fidelity. But in rendering for learning, The observer is a machine learning model. Our focus is to shape a useful training distribution. But this means that the fidelity alone is not enough. We should also ask whether the data actually improve downstream utility, such as segmentation and detection performance. When we design the synthetic dataset, the part we can directly control is the modeling and rendering parameter space, like defect type, material, lightning viewpoint, and sampling rate. But in practice, choosing these parameter ranges is often based on our intuition, so we can look at the pipeline from another perspective. In our pipeline, we first sample parameters to create different scene setup. Second, render images. Third, extract features using a pre-trained vision model. Here are the 2D projections of the feature space. Then train a task head. Finally, get the output. When designing a dataset, graphics practitioners may focus more on the parameter space and image space. But downstream model does not directly see them. It learns from the extracted features. So we move comparison to feature space, which is closer to the final output. Our assumption is that useful synthetic defects should show meaningful behavior in feature space, relative to real defect samples and nominal samples. Based on this, we screen data in feature space before training. Let's take a closer look at feature space. First, we map all real defects and nominal data from image to features and references. Then we cluster real defects into different modes. Next, we embed synthetic defects into features. A natural idea to select synthetic defects that are close to real defects. However, this alone may make the selected set collapse to a single defect mode. So we add a coverage term. This encourages the selected set to cover multiple different defect modes. However, this may still select samples that are hard to distinguish from nominal data. So we add a separation term to push the selected synthetic defects away from the nominal samples. Overall, we first generate a large synthetic candidate pool, then select a useful subset, considering measures of alignment, coverage, and separation to describe the feature distribution. To build the candidate pool for screening, we first identify the key modeling and rendering factors, vary them over broad parameter ranges, and then render the candidates. Let's start with the defect modeling strategy. Here we compare 3 procedural approaches: geometric-based, bump-based, and texture-based modeling. A natural expectation is that more physically explicit method should always work better. However, this is not what we observe. In our setting, the bump-based approach actually achieves the best performance. We evaluate the downstream performance using the F1 score, so which balances false positive and false negative. A higher F1 indicates better detection performance. So the takeaway is more physically explicit modeling does not necessarily produce more useful training dataset. Then let's look at the defect morphology. This is one of the most important factors because morphology decides which defect modes exist in the generated data. For example, if the detection target is the denomination, synthetic denomination samples are helpful because it covers the relevant mode in feature space. But if we generate scratches or dents, they may look like defects, but they do not cover the right defect mode for the task. As a result, their downstream benefit is much smaller. So we need to make sure the correct defect morphology is present. Next, we consider the visibility factors, material, viewpoint, and illumination. These factors determine how visible a defect appears in the image, and therefore where it is represented in the feature space. If a synthetic defect becomes visible in a similar way to real defects, its feature representation tends to move closer to the real defects. Unlike defect morphology, these factors do not create new defect mode. Instead, they mainly changes how clearly the defect can be seen and how well it stands out from the local background. Finally, we look at the sampling rate. Unlike morphology or visibility factor, SPP mainly changes the spread of the feature distribution without substantially changing its overall distribution structure. Interestingly, higher SPP does not always need a better downstream performance. A possible explanation is that moderate noise may improve generalization, while very clean synthetic images may reveal modeling mismatch more clearly, since there is always a domain gap between synthetic data and real data. So we don't always need expensive high SPP rendering for synthetic data generation. These observations give us a practical order for dataset design. We can first use cheap and flexible modeling approach to cover relevant defect modes. Then we choose material, light, and view settings that make the defect visible and separable. Finally, we choose a reasonable sampling rate to reduce the rendering cost. So the whole pipeline can be summarized in 4 steps. First, we sample from broad parameter ranges of the K modeling and rendering factors and render a large candidate pool. Second, we extract features from both real and synthetic images and embed them into the same feature space. Third, we score the candidate defects using our 3 measurements: alignment, coverage, and separation, and select the most useful subset. Finally, we train the downstream model use only the selected defect samples and test it on the real data. So instead of using every rendered image, we screen the synthetic data in feature space before training. For the experiments, we evaluate the method on 4 industrial objects. The amount of real data is limited, especially for the end mill top case, where we only have 5 real defective samples. For screening, we use Dilo backbone as feature extractor. So Dilo is a widely used pre-trained foundation model for segmentation task. And the L6 is an intermediate layer to provide a balance between local detail and semantic abstraction. Here are the results. There are 2 main findings. First, more synthetic data is not always better. This is especially important when real reference data is very limited. As more synthetic defect samples are added, less informative examples may gradually reduce the quality of the training data. Second, the results show that our screening heuristic improve the performance. Compared with random selection, feature-space screening tends to select more informative synthetic samples and leads to a better downstream performance. Then let's do the conclusion. There are 3 categories. First, synthetic dataset generation can be viewed as a feature distribution design problem, rather than simply maximizing the visual fidelity. Second, different modeling and rendering factors play different roles in shaping that feature distribution. Finally, compared with random selection, Feature space screening selects more useful synthetic data for downstream training. There are also several limitations. First, our framework depends on the choosing feature representation, but it will benefit from stronger feature representation as they improve. Second, further improvements in sample selection could help better capture the feature distribution. Finally, a natural next step is to use feature space feedback to guide the parameter exploration during dataset generation, closing the loop instead of only screen the candidates afterwards. Thank you for your attention. I'm happy to take any questions.
Are there any questions?
So could you explain, because I don't know anything really about the defect, this data set creation, how costly it is to, for example, create real data versus your synthetic data set? Could you elaborate a bit on that, the actual cost of, say, creating a data set that you're currently using in this paper?
Oh, you mean the cost for modeling the defects?
Yeah, and also generating the...
Yeah. So usually we first have the acquisition set up in real industrial factors. And usually we can know some camera set up and lighting set up. But for the materials, usually we don't know very details. So we first, for the visual setup, we can acquire some imaging set up from the camera and lighting. Then for the surface, we just use our some background knowledges to use some Perlin noise, Voronoi noise, to modulate to model the textures. Then we have the textures, because textures is the nominal data. Then we model the defects. For the defects, we have some knowledges from the factory, because they will provide we may in this product we might have scratches, and we might have the cracks, and we might have the denominations. Then we know some types. And also they might provide some reference. Then we use that to generate realistic looking images. In previously, we have a thought we must generate a very realistic looking images. So we use very high SPP, we use very fancy modeling and rendering technique to make it very realistic. But finally we find, this might be important for our human eyes, but this might not very helpful for the model training. The vision model may focus on the morphology, so this is a key factor for them. And also for SPP, maybe we think this is noise, this is not good, but but for the machine vision model, they might think, this is might help for generalization, because this noise can naturally provide some provide some variations as the regularization.
Yes, so in this work, you actually reduce the cost of generating it by a lot.
Yeah, so when we know which factors are important, we just vary these key factors to expand a very large synthetic data set. Then the graphics practitioners, the dataset generator, the dataset designer, they don't need to think about, for the roughness, what's the ranges we need carefully design.
Yes.
They just generate a broad ranges, generate many data candidate pool, then use the feature space screening measurements to select a useful one for training.
Thank you very much.
All right, we're at time. Yeah. Thanks. Let's thanks again all the speakers.